Hello, I'm Rob Higuerita, and I'm an enterprise support lead at AWS, and I'm based out of Austin, Texas. Welcome to AWS Supports You, where we share best practices and troubleshooting tips from AWS Support. Joining me today is Rob Yang and Mike Percy from AWS Support. Can you give us a quick introduction, Rob, and then Mike?
Sure. Hello, everybody. My name is Rob Yang. I'm a technical account manager located in Calgary, Alberta, Canada, helping AWS enterprise support customers be successful on the cloud. I'm also a specialist in management and governance, focusing on cloud financial management. Can't wait to talk about a few things about Lambda cost optimization to the audience here today. Mike?
Thanks, Rob. Yeah, my name is Mike Percy, and I'm an enterprise support lead. I'm also based out of Calgary, Alberta, Canada. And one of the responsibilities that we have as technical account managers is to help our customers optimize their costs. And I'm really excited to talk to you today about how you'll be able to do this with AWS Lambda environments. So thanks.
Great, thanks for the intros. So today we'll be introducing you, as you mentioned, to cost optimization best practices for Lambda, as well as some architectural best practices to optimize performance. But before we get into the details, just a quick note to the attendees online. Please feel free to use the chat window on the right-hand side of your screen to share your thoughts and ask questions today of Rob and Mike. They're here to answer them and kind of give you that one-on-one option to chat with them. So I really look forward to hearing from you all. So Mike, can you walk us through what we're going to be talking about today?
Yeah, so today we're going to be focusing on cost savings with AWS Lambda primarily, and we'll be looking at cost optimization and management from a number of different angles, including code optimization and how we can profile Lambda functions to optimize performance. And Rob's going to take a look at Cost Explorer and tagging practices, and then discuss some of the architectural best practices to help ensure optimal performance of your serverless environments. So let's get started. So when we are talking about serverless, what do we mean by that? And when we say serverless, we're really talking about applications that are built with technologies that eliminate the need to manage servers, that can scale to nearly infinite automatically, and you pay for what value you get out of it pricing model. And these systems are also highly available automatically. And this strategy is often referred to as a serverless operational model, and enables you to really drastically reduce the time spent on things that aren't core to your business. So you can reduce that undifferentiated heavy lifting and focus on the products that really drive value for your business. And we've got a number of customers that have made the decision to achieve this value through a serverless first strategy, and or a decision to use serverless services as a preference. And unless there's a use case for it that the workload really demands that they choose otherwise. Some of these customers like iRobot, Alma Media, and Fender are all serverless first. And when we start out and developers are toying around and getting started with Lambda functions or using it for cron jobs, they're probably incurring such low costs that the pricing model doesn't really have a lot of impact on the business. But as you start to adopt a serverless first strategy, or start using serverless more, you might need to recalibrate. And rather than overpaying for pre-provisioned servers, your costs align to usage. And now you really need to start thinking about how you're using your systems in parallel and managing your costs. So when we're talking about serverless, we're also talking about more than just compute. And while Lambda is typically the service you think of when we mention serverless, we have many other services across different layers of the stack that will be connecting to AWS Lambda. And for data storage, we often see things like Amazon S3, Amazon Aurora Serverless, and Amazon DynamoDB as data stores. From an integration point of view, we typically leverage Amazon API Gateway to publish our APIs, and leverage Amazon Event Bridge, Amazon SQS, Amazon SNS, and AWS Step Functions to help with communication and orchestration of the solutions. For our discussion today, we're really going to be focusing on AWS Lambda, but we'll also touch on some of these integration points in the architecture section and how to best integrate with these other services such as S3 and API Gateway. And while Lambda offers many key advantages for our customers, it's really when all of these components surrounding Lambda come together that we really see much bigger benefits. Messaging, orchestration, storage, and compute all together are really the secret sauce that make serverless magical. During our presentation today, we're really going to discuss how to optimize and manage costs with AWS Lambda and how that integrates into some of those other serverless technologies that we just described. Rob, did you want to maybe take a moment and start us off with the management and governance side?
Sure. Thanks for the intro, Mike. Let's start by talking about cost optimization for serverless based on our well-architected framework. As covered in the AWS well-architected framework, the increased flexibility and agility that cloud enables encourages innovation and fast-paced development and deployment as well. It eliminates the manual process and time associated with provisioning on-premises infrastructure, including identify your hardware specification, negotiating price quotations, managing purchase orders, scheduling shipment, and so on. So we can't really start talking about cost and cost optimization without the mechanisms of being aware of the cost first, allocating it, and owning it. As your serverless architecture grows, the number of Lambda functions, APIs, stages, and other assets will multiply. Most of these architectures need to be budgeted and forecasted for in terms of cost and resource management. And tagging can help you right there. You can allocate this cost from your AWS bill to individual functions and APIs and obtain a granulated view of your cost based per project or application, your AWS Cost Explorer. A good implementation is to share the same key value tag for assets that belong to the same project or the application programmatically and create customer report based on the tags that you have created. This feature will help you not only allocate your costs, but also identify which resources belong to which projects. After that, you can show back or charge back to your business unit depending on your internal accounting model. So the owner of the projects and application is aware and responsible for the cost. In the end, the whole process drives responsibility and efficient behavior. So let's take a look at Cost Explorer. Many of you may be familiar with Cost Explorer already, which has an easy-to-use interface that lets you visualize, understand, and manage your AWS costs and usage over time. On the right-hand side, I've got the filters for Cost Explorer on the screen. I'm going to show a quick example. I filtered down the cost by several services, including DynamoDB, Lambda, S3, and going down there's a filter for tag. Here is where you can select your tag related to a specific project or application, as we talked before. An important note, the tag keys listed here are not any tag. They need to be cost allocation tags. So in your AWS Billing Console, on the screenshot on the left, you can activate regular tags to be cost allocation tags. For example, if you have never used cost allocation tags in your AWS account before, and you tag your S3 bucket with the key as project and the value as serverless experiments, for example, you will need to enable the tag project in cost allocation tags before it can be used as a tag filter in Cost Explorer. One last note, like tags are case sensitive. So project with a capital P is different than the project with a lowercase p. So just be aware of that. Rob H., do we have any questions from the audience?
Hey, Rob. Yeah, we don't have any questions from the audience right now. So audience, please make sure to put your questions in if you have any about our AWS Lambda. But I do have a question. Since you're mentioning taggings, what's the best way to tag existing Lambda functions in batch?
Right. So for existing functions that you haven't tagged, so the easiest way would be to go into resource group and tag editor. So if in the search bar after you log into AWS console, search for resource group and tag editor. So in there, you can tag your resources in batch, I think up to 500 resources at a time. So that's a good way you can tag existing Lambda functions or any other resources for that matter.
Great. Thanks, Rob. Appreciate it. Back over to y'all.
There we
Okay,
go.
Mike.
All right. Yep. Looking for the mute button. For code optimization, let's spend a few minutes and look at what we can do here. To start out with, let's just do a level set on how is Lambda priced. And when we launched Lambda a little bit over 5 years ago, we had two different pricing dimensions. So it's really based around requests and duration. And you're charged based on the number of requests of your function and the duration and the time it takes for the code to run. So Lambda counts each request each time it starts executing in response to an event notification or an invoke call. And this includes test invocations from the console. And duration is calculated from the time your code begins executing until it returns or otherwise terminates. And this is now based on per millisecond billing. So the total amount of time is calculated for each invocation. Basically, the other piece to this is you allocate the amount of memory you want to your function. And as that is allocated, you're also allocating a proportional CPU and other resources to that Lambda function. And so we'll look at how that impacts the performance of the overall function and how fast it is able to execute. An increase in memory size triggers an equivalent increase in CPU that's available. And we'll look at how that can improve the performance. And
Mike, don't forget about free tier pricing.
Yeah, absolutely. We do have a free tier available as well. And you're able to get 1 million free requests per month as a starting point. And you get 400,000 gigabit seconds of compute time. And we're really going to focus a lot of our cost optimization discussions here really around the duration and memory sizing as our area to focus today, because the requests are going to typically be part of your architecture point of view, but the duration is something that we can have a lot of control over, and we can look at some ways that we can streamline that. So when we look at this, let's talk a little bit about global scope. And each time a Lambda is executed, there's two sections that are executed. The first part here is what I'm calling the global section. And the global section is only launched the first time that the Lambda function is invoked. And so the next time, after it executes the first time, it sits there and it waits for a follow-up initialization to see if it's going to get used again. And then if it is, then it will only execute the handler function portion. And so that will allow the second part of the code to run through each time. This allows the global scope to handle kind of the more expensive one-off operations. And some examples of this would be things like connections to databases or initialization logic and that sort of stuff. When we're able to put that into the global section, it'll persist, and then the next time we don't have to have that expensive operation in the global section. We'll handle it inside of the handler function instead. So let's take a look at what this looks like. And so what we've done is we've created two Lambda functions. So we've got two identical Lambda functions, and we're going to basically race these two functions against each other just to see what kind of difference this makes. So these Lambda functions are going to make a call to a DynamoDB table. And inside the DynamoDB table, we've got a list of movies that are available in there. And we're just going to retrieve at random a year and pull the movies from this table. The only difference that we're going to have with this code is where the DynamoDB connection initializer is located. So we're just going to move it from the handler function in the get movies into the global area for the get movies _ global. All right, so we'll get started here and we'll open up the AWS console. Okay, and first thing we're going to do in here, we're going to go in and we're going to open up the Lambda console. Go, and we've got our two functions listed here. And so we've got movie by year and movie by year global. So we'll open these up in tabs here. Okay, perfect. Okay, we'll open up the code. Okay, so in here you can see we've got our Lambda initialization in the query movie function. And we're going to call that in our Lambda handler. And there's the DynamoDB initialization string. So that's going to be, every time we run through this, it's going to create a new connection to Dynamo. So what we'll do, we're going to just run a couple test runs here. So the first one is going to be a cold start, most likely. And so this is going to show our duration for our initial runtime. So this one took 2,500 milliseconds to execute, and you can see that there. And you can see here on the size of this one, it's 128 megabyte Lambda function, and we're using about 96 megabytes on this one. So let's run it again. This should be a reuse of the environment here. And if we look at our duration here, we can see that that drops quite significantly. We're down to about 537 milliseconds. And no change in terms of the size of the function or really the amount of memory used is pretty similar. Okay, so next, let's switch over and look at the movie by year within the global function. So you can see here that we've basically moved only the one line here. We just moved this up into the global section, and you can see we've commented it out inside of the query movie. So this is only going to initialize on the first time we run it, and then subsequent times it will not. So let's run a test here. We'll scroll down here. So we can see the cold start here took about 1,229 milliseconds. Still 128 megabyte size Lambda and 97 megabytes this time. And then we'll run it again here. And so this one ran much quicker. It took 146 milliseconds this time. And you can see here, again, memory is basically the same. So that's interesting, but let's actually go and take a look at a much broader data set, because this will let us see what happens over quite a bit of time. So we'll open up CloudWatch, and we're going to go into CloudWatch Insights, and we'll take a look at averages of several thousand runs of each of the functions, so we can see how they perform differently and get an idea of it as it scales over time. So we'll go into CloudWatch, open up Log Insights. And I've got some saved queries here. Mm-hmm. So let's look at the movies by year first. Okay, and I'll expand this out here. Okay, and I'm just going to remove this last line here. This just would put it into per hour buckets so that we could see how it averages per hour, but we want to look at this as a whole. And we'll change this to, let's say, a week. Okay, and we'll run the query here. So this is pulling back about 4,000 different requests. And it's going to give us an average runtime here of 506 milliseconds. So this is for the unoptimized version at this point. So let's do the same thing now for the movie by year with in the global function. Keep it at 1 week. We're going to delete out the bin again. And this time we're going to get about 3,000 executions. And you can see here, just by moving that one line of code, we've got an average runtime now of 220 milliseconds. So, we've gone to below 50% of the runtime on just by moving that Lambda or DynamoDB initialization string into the global function area.
Yeah.
So what does that mean in terms of cost? So I think if we switch back to our PowerPoint presentation now, we can look at the example of the cost difference. So let's use some theoretical numbers here. Let's imagine that for our movie database, we had 100,000 users that we're using our application. And we've got 20 invocations happening per day. And with 30 days in the month, that's going to generate 60 million invocations. And so that's our first part. And you remember that we've kind of got the number of requests, and then we've got our duration. So for the request side of things, we would take our 60 million invocations. It's 20 cents per 1 million requests. So that would work out to $12 for the month for this function. So that's fine. Now let's look at what it actually costs to run with the different performance or different speeds. So at 506 milliseconds, we've got 60 million invocations times 506 milliseconds. And then our cost for a Lambda function with 128 megabytes is this very small fraction of a penny here per millisecond. So that works out to $63.75. So if we add the $12 to the $63, we end up with about a $75.75.6. So if we look at the global variable, by moving this into the global variable side of things, we still pay the $12 for all of our invocations because that isn't going to change. But what we do see change is our cost drops down to $27.72. And we end up with a total cost then of $39.72. So total reduction in cost is works out to about 48%. And all we've done is we've moved one line of code, the Dynamo Boto 3 initialization piece, a few lines up in our code in order to get that optimization. And when we look at Lambda, it's a small effect on this one function. But if you have hundreds, thousands, tens of thousands of Lambda functions in your environment, these small effects compound on each other and add up over time.
That's right. Impressive.
So in addition to this, so let's talk a little bit about another way that we can also improve performance in our environment. So in addition to being cost effective by leveraging the global scope, another way that we can go about being cost effective is also being really careful about how we select libraries and what we load into our Lambda environment. So again, when it initializes, it's going to have more overhead with more the more the libraries that we load into it. So a good example of this here, where we're using our JavaScript SDK. We're loading in the entire AWS SDK in our first section here and creating a connection back to DynamoDB. If you are just going to be talking to DynamoDB, we don't need all of that extra overhead from the full AWS SDK. So if we change our code and we load in just the DynamoDB client, we're able to, again, further speed up and optimize our Lambda environment. And remember that because you're paying per millisecond, every time you save a millisecond, it's money that you're keeping in your pocket. And so to give you an example, I'm not going to run through and do an example on this today with the loading the libraries, but we ran through and did the same sort of experiment here, and we were able to reduce the cost of the function by 25% on this, and basically reduce the runtime from 175 or 77 milliseconds to 133 milliseconds in the test run-throughs that we did. So again, a very small change that you can implement into your code, get your developers using, that can have good returns for you across your Lambda environment.
Sorry. Do we have any questions from the audience? Rob H.
Hey, Rob and Mike. Thanks. Yes, we actually did have one that just came in from Ray_DB222. Ray wanted to know, can I load my own libraries in Lambda?
Yeah.
Yeah.
So do you want to take it, Rob? Or?
Sure.
Okay.
Yeah, so I think yes, you can. The short answer is, and you can do that in several ways. So one way is to, you load your library and you zip it up and upload to Lambda, or alternatively, you can use layers in Lambda. So you load your own library in a Lambda layer, and you use that in your Lambda function. Mike, anything to add?
No, I think that covers it well.
Great, right? Thanks. That's all for right now.
All right. Okay, so let's talk a little bit about how we can profile and optimize our Lambda functions. And we've got a tool inside of AWS, AWS Compute Optimizer, which is designed to recommend optimal AWS resources for your workloads and reduce costs and improve performance by using machine learning to analyze your historical utilization metrics. And it's going to look at over-provisioning of resources that can lead to unnecessary infrastructure costs and under-provisioning of resources that can lead to poor application performance. And Compute Optimizer helps you choose the optimal configuration for 3 different types of AWS resources. So EC2 instances, Amazon EBS volumes, and Lambda functions. And it's all based on your utilization data. So if in my account, I went through and I ran this, and it was able to identify 2 under-provisioned Lambda functions that I had. So by going in and increasing the size on these, it would improve the performance of my Lambda environment. So this is a really powerful tool. There's no cost associated by enabling it in your account, and it can give you some good guidance as to how to optimize your serverless compute. So we've got another tool that I wanted to talk to you about that's available, and this is an open source tool that's available on GitHub. AWS Lambda Power Tuning is a state machine powered by AWS step functions that helps with optimizing your Lambda function for cost or performance in a really data-driven way. And at AWS, that's one of our favorite ways to drive decisions. So we'll talk about how we can go through and deploy this in your environment, but it's basically a step function that will invoke your Lambda functions at different configuration sizes, and you can go through and specify the size of the different Lambda functions you want to test it. And it's going to come back with suggestions to maximize performance or to minimize costs on this. And this will actually use real requests against your Lambda function, so it can really see how it's performing and give you some ideas as to what you should do in terms of sizing on this. The nice thing too is this also can create some really great visualization, so you can see what is happening in your Lambda function as you change the size of the compute power or the memory on your Lambda function. So if we look at this, I ran our get movies function through the tool here, and I'll show you what the output on this looks like. We've got basically 2 lines that it generates. And so the red line is our execution time. So we can see as we increase the amount of memory on this, the first data point here is our 128 megabytes of memory, 256, and then or 512, I think. Yeah, 256, 512, and then 1024. We can see how the runtime decreases. And that's going to be partly related to adding more memory to it. And then when we add more memory, that adds more network resources, it adds more CPU resources. The blue line shows us the cost benefit on it. So we can kind of look at this and we can figure out where our best cost is based on that. And we can see here that our lowest cost point is at the 256 megabyte size. So that is where our best cost performance is for this particular function. Anything beyond that, we start to creep up in cost, and start to get minimal returns in terms of how fast it completes function. So let's maybe take a few moments, and what we'll do is we will, just give me a second here. And what we'll do is we'll go through, we're going to do a demo on how to deploy this tool to your environment, and we will run our other Lambda function through this and see how the global function looks. Okay, perfect. So we're going to go into the AWS Management Console. And in here, we're going to open up the serverless application repository. Okay, and then in here, we're going to go into available applications. And we're going to do a search in here for AWS Lambda power tuning. Okay, and one of the things, if you don't see it, make sure you've checked off the box there because it does create IAM roles. It won't show up otherwise. Okay, perfect. So we're in here. So now we've got a bunch of application settings that we can set for this, and they're described in the README file on the left. We're going to check off that where you acknowledge it's going to create IAM roles. And then we will start the deployment. And we can also set some security boundaries around this because it is going to run our Lambda functions. We can set what Lambda resources it's allowed to use. And we can also set some permission boundaries as well to help control and prevent problems. And so while this is provisioning here, we'll look and see, okay, yeah, deployment is running. And so this is going to take about 45 seconds. And so the serverless application repository is a managed repository for our serverless applications. And it enables teams and individual developers to store and share reusable applications and easily assemble and deploy serverless architectures in new ways. And using the serverless application repository, you don't need to clone, build, package, or publish source code to AWS before deploying it. Instead, you can just go and grab pre-built applications from SAR. And each application is packaged with an AWS Serverless Application Model template, so SAM, that defines the AWS resources used. If it's publicly shared, it's also going to include links to the application source code so that it'll be accessible to you. So let's just see where we're at here. Should be done here in a second. There we go. Completed.
Yep.
And so now what we're going to do, let's go over and open up step functions. And we'll see in here, we'll have our power tuning state machine.
Mm-hmm.
Okay. All right. And so let's go in and we will start an execution. And what we'll do is we will copy and paste our JSON file in here. So this is going to use a JSON file to define what we're testing. And we can see here that we've got the Lambda function ID. We can pick and choose the sizes of the power values we want to test. And if it requires a payload, we can put the payload in here for the Lambda function. Ours don't. And then we can set a strategy. So we can choose either a cost allocations optimization strategy. We can choose a performance, or we can choose a balanced option in here. We're going to choose cost because that's what we're concerned about today. And now we'll let this run. And so while this is running through, it's going to initialize each of those Lambda functions a number of times to come up with our metrics here. And because this is a step function and it's all JSON driven, we can look at this tool and we could integrate this into our CI/CD pipelines. So as your developers are going and deploying new Lambda functions into the environment or updating them, it can go through and as part of that process, optimize and figure out what the best size is for the function and automatically size them appropriately. So it can be a great mechanism for you to save some money automatically.
Mm-hmm.
So we've completed the execution on this. And so if we go to our execution output up above here, we'll see the output from this. So it'll show us the size that it's recommending, what the cost is to run the function. And it gives us a link here that we can go and look at the chart that we had previously seen earlier. And so we'll put this into our browser. There we go. And so we can see here what the footprint or the thumbprint of this Lambda function's performance looks like. So we can see here in this case, from a cost perspective, this one actually works out better at the 128 megabytes for it. It's kind of interesting to see how this one differs from the previous example, in that for the 256 megabyte size, it actually performs slower than the 128 megabyte or the 512. So it's kind of interesting. You can't necessarily assume how the Lambda function is going to perform. So this is a really great tool to go and get a good understanding of what it looks like and where to size things. So really easy to use. You can also give your developers the ability to go into the step function. They can put their own JSON file in there. But on the GitHub link that is accessible, you can actually go in there and create a web front end for this as well, if you want to give your developers that sort of access, so they can profile functions through development. So some great tools for them.
All right. Thanks, Mike, for the demos. So
Yeah,
now I'd like
absolutely.
to go through a few architectural designs on serverless and how builders can be aware of the cost of them. So adopting the guidance can enable you to build and operate cost-aware systems that achieve business outcomes and minimize cost, allowing your business to maximize its return on investment. And generally speaking, serverless architectures tend to reduce the cost because some of the services, such as AWS Lambda, don't really cost anything while they're idle. However, following certain best practices and making trade-offs will help you reduce the cost of these solutions even more. I'd like to go through some scenario with you about waiting in Lambda functions. That's the first one I'd like to talk about. This is something you might want to be aware cost-wise. Within a single Lambda function, you want to ensure any potential concurrent activities are not scheduled synchronously. For example, a Lambda function might write to an S3 bucket and then write to a DynamoDB table. The two-way states shown in the red on the diagram are compounded because activities are sequential. So how do you break the pattern? Well, if the tasks are independent, that means they can be run in parallel. Running in parallel would result in the total wait time being set by the single longest running task, not added together. Now, the S3 put object and the Dynamo write item calls are running independently of each other and in parallel, so the wait duration is reduced. Now you may ask, what if my second task is dependent on the completion of the first task? So my DynamoDB writes need to be done after I make sure S3 put is complete, right? I can't really start the second one if you can't make sure the first one is absolutely complete. So in that case, where the second one depends on the completion of the first one, you may be able to still reduce the total waiting time and the cost of the execution by splitting the Lambda functions. In this design, the first Lambda function responds immediately after putting the object to a S3 bucket. The S3 service invokes the second Lambda function, which then writes data to the DynamoDB table. In this approach, it minimizes the cost wait time in the Lambda function runs. Secondly, this model doesn't adopt well for serverless development. So think a simple e-commerce application this time consists of 3 Lambda functions that process an order. First one, create an order. Second one, process the payment. And then the third one, produce a PDF invoice. The cost-wise with Lambda, you pay for the duration of an invocation. So in this example, while the create invoice function, the third one runs, the two other functions are also running in a wait state showing right on the diagram. Now, most programming languages support the concept of code synchronously calling functions within a code base. In this case, the caller waits until the function returns a response. This happens on a traditional server or a VM. Your operating system scheduler switch to other available work. Since they already, quote unquote, own the server or VM, whether the CPU runs 0% or 100% doesn't really affect the overall cost of your application. You're just paying for the fixed cost of owning and operating a server. However, in serverless world, example of the three functions here, while this synchronous flow may work within a single application on a server, it introduces several avoidable problems in a distributed serverless architecture. And one of the biggest problems is cost. With Lambda, you pay for the duration of an invocation. So in this example, right, you introduce lots of waiting as shown in the red. And there are also other problems, such as the tight coupling of these functions. It introduces scaling problems and error handling problems. So let's take a look at the cost. So how do we redesign it? Well, you can decoupling using Amazon SQS or using AWS step functions. So there are two common approaches to avoid these patterns, right? SQS queue would be one. So you add a SQS queue between your Lambda functions, especially decouple the two functions that introducing your wait states. If a downstream process is slower than the upstream process, the queue durably persists. In this example, create order function publishes a message to an AWS or Amazon SQS queue, and the process payment function consumes the message from the queue. The wait time is reduced as the first function, create order, is no longer waiting for the downstream function to complete, cutting unnecessary running time. The second function, process payment, will then publish its response to an SQS queue. Whether the payment is successfully processed and the invoice is successfully created, you need to design a mechanism to check the status of them, right? You can further decoupling your second and third functions using the same technique with SQS. That being said, when your system or business logic get complex, handling the response checking after decoupling all the functions may become sort of unmanageable. Then you can use the second common approach, which I mentioned earlier, AWS step functions. For complex process with multiple types of failures and retry logic, step functions can help reduce the amount of custom code needed to orchestrate your entire workflow. As a result, step function orchestrates the work and robustly handle errors and retries. And then your Lambda functions contains only the business logic, not the waiting. So let's have a quick look at step functions. You can try implement the design without waiting in Lambda at all using AWS step functions. Step functions is a serverless function orchestrator that makes it easy to sequence AWS Lambda functions and multiple AWS services into a business critical application. As in the previous e-commerce application example, it has long-running process tasks, such as processing payment, for example, where you may need to wait for the task completion before processing to the next step. This wait state may be implemented within the Lambda code, but is far more efficient to either transform the asynchronous processing using SQS or implement the wait state using the step function shown here. For this example, in this step function state machine, we pull the payment process and review its states every 30 seconds. Just as an example, we can do more frequent than that to see if it has finished. So instead of coding this wait within the Lambda function, we implement this pull, decider, and wait states. Implementing a wait state with step functions won't incur any further cost, as the pricing model for step functions is based on the number of transitions between the states, not on the time spent within a state. So waiting in a state doesn't cost you anything for step function. depending on the integration, you have to wait. Steps functions can also wait synchronously before moving to the next task, saving you an additional transition. Say if the e-commerce application needs to make sure the payment is processed successfully, the invoice is generated and the order is created in the system before sending out an email confirmation. So rather than pulling the result, the wait for the final confirmation can also be done within the state machine before it ends. There's one last example I'd like to show, which is the recursive pattern that may cause your Lambda function runs away. Generally, service or resource that invokes a Lambda function should be different to the service or resource that the function outputs to. So failure to manage this can result in infinite loops or runaway Lambda functions and drive up your cost. In this example, a Lambda function writes an object to an S3 bucket, which in turn invokes the same Lambda function via a put event. The invocation causes the second object to be written to the bucket, which invokes the same Lambda function, and it goes on. This happens because triggering a Lambda function where an object is created in the S3 bucket. This is the same case for DynamoDB when a table is updated. So having the function modify the data in place will trigger the same Lambda function again. So effectively an infinite loop again. So both Lambda, S3, and DynamoDB automatically scale based on the traffic. So the loop may cause your Lambda to scale up really much and consume all the available concurrency S3. And S3 will continue to write objects and generate more events for the Lambda, right? So what can be done to avoid this situation? In the event of your it happens to you and you discover that a Lambda function is running away, you want to stop it running first, right? So use the throttle button in your Lambda console to scale the function concurrency down to 0. It effectively breaks the recursion cycle. It's like pressing an emergency stop button. This example uses S3, but the risk of recursive loops also exists in DynamoDB, SNS, SQS, and other services. In most cases, it's safer to separate the resources and produce and consume events from Lambda. So use a new S3 bucket to store and modify the output file from the Lambda function. This would be the simplest solution. S3 storage cost is by the size across all your buckets in an account, not by the number of buckets you have. If you have specific use case that you need a Lambda function to write data back to the same resources that invokes the same function, ensure that you use a positive trigger. For example, an S3 trigger may use a naming convention or a meta tag that is only triggered on the first invocation. So this prevents object written from your Lambda function invoking the same Lambda function again, right? And there are some other techniques can help you with this kind of scenario. So you can use reserve concurrency. Reserve concurrency, you set your function with reserve concurrency to a lower limit that prevents the function from scaling up beyond that limit. It does not really prevent the recursion, but it limits your resource consumed by using a safety mechanism. So this can be useful during deployment or test phase. So for example, if you set your reserve concurrency to 10, as an example, the Lambda function will not scale beyond 10 running concurrently. Or third, you can use CloudWatch monitoring and alarming. You can set up some logic. Once your CloudWatch triggers an alarm when it detects your concurrency went beyond a certain point, you can do some automation, such as an automated runbook to actually scale down your Lambda function, prevent this from happening. There are two important links that we'd like to share today and guide you through your journey to serverless and Lambda. We still have a few minutes to take any question you may have. Rob H., any questions from the audience?
Hey, yes, we do have one question that came in from MonRamon357. Welcome back. Is there a charge for deploying functions as containers in AWS Lambda?
Perfect. Yeah, I can take that one, Rob.
Yeah.
So containers support has been added to Lambda, so you can deploy Lambda functions as container images up to 10 gigabytes in size. In terms of costs around those, there is no additional cost for using that feature, but you do pay for the ECR repository and then your normal Lambda pricing, so duration and number of requests.
Great, thanks, Mike. Appreciate that. So everyone, today we looked at cost management for AWS serverless technologies. We looked at primarily looking at the cost savings for AWS Lambda, as well as some recommended architectures that can help you to optimize costs and improve performance. If there's any questions that were not answered today, you can post your questions on forums.aws.amazon.com. And please feel free to email us any feedback or show topics to awssupportsyou@amazon.com. We really want to hear from you. Tell us what you think and we'd really like to see here. And thank you again for joining us at AWS Supports You. Happy cloud computing.
Thanks, everyone.
Yeah.